Yeah, just one thing. Actually, Professor Thompson here said he wants to have Professor Thompson wants to have each other. Yeah.
There is nowhere near. That's why
I don't need to watch it.
I'm thinking autonomous because it is on long time. And
Are you wearing the microphone?
Yeah.
No.
Yeah, he emailed director.
More important.
This is comparatively significant than considering the climate change for next 20 years. That's not like, what do you think, Sean?
Yeah. Okay.
You ready?
I don't know.
I don't know. Okay. I'm going to tell them that you have to give me idea.
Yeah.
Ready? Okay, good afternoon, everyone. Today, our Ken lecture is going to be divided in two sessions. Both presentations related to transportation geotechnics.
Sorry.
Can you turn it on? So first we're going to have Huang, who graduated with his bachelor's degree from Shenyang University in China. His master's degree is from here, from UIUC. He's currently working under the supervision of Professor Errol Tutumler in imaging techniques for granular materials and the associated size and shape analysis. On the second portion of the lecture, we're going to have Qamhia, who graduated from his BS from Berzit University in Palestine in 2012, and then from University of Wisconsin at Milwaukee in 2014 from his master's degree. Currently, he works under the supervision also of Professor Errol Tutumler, and his research focuses on the utilization of aggregate Quarry By-Products in sustainable pavement applications and the evaluation of their performance as a base, subbase, and subgrade material. Please, let's welcome both our speakers.
Hello, everyone. Hello, everyone. I'm Huang from Dr. Errol Tutumler's research group, and today I'd like to share some of the progress we made on the ICT R27-182 project, known as the REPREP project. So my topic is the field imaging and volumetric reconstruction of REPREP material and large-size aggregate, from algorithms to application. First, Jiayi Luo and I are the two grad students in the research group on this project. Mazia Malvani are the previous postdoc in our research group, and John Hart from Beckman Institute, a research engineer, and my advisor Errol Tutumler. Also, Sheila Bashirs and Andrew Stoba are the IDOT TRP chairs of this project. And for those who are familiar with the image analyzer in the soil lab, this research actually starts as an extension of that technique. But till the end of this presentation, you will find the approach are sort of different, and the thing we have in mind is actually way larger than that. So I will start with a problem statement. So the problem this research tried to solve is for those large size aggregate at quarry site, how can we quickly and reliably determine its size and shape with less labor intensive way and a more objective way? So take this image for example, how can you easily define its size, volume, and shape of those aggregates in that? And that's the key problem we are trying to solve. My presentation will follow this outline. First, I will start with some introduction and motivation of this project. Then the two algorithms we developed, the color-based image segmentation algorithm and 3D volumetric reconstruction algorithm. Then we'll introduce a field imaging setup and some ground truth measurements. Finally, we come to the result and discussion part with some conclusions and recommendations. So I'll start with the introduction. So the REPREP material, like in the figure, is actually the most common type of large size aggregate we have in industry, and the most front-end product at quarry sites. these pictures are collected during last summer in a field trip we made, and that's actually the typical quarry operations by using a crusher to crush the crude stones into different sizes. And the different sizes controlled by the crusher size are separated down like that at the quarry site by separating them into R1 to R7 with increasing the particle size. And riprap materials are usually used in many hydraulic infrastructures like bridges and shorelines because it has great durability against scour and water ice erosion. So this typical usage includes spring bank rebatment, bridge pier to stable the bridge pier, and at the bridge abutments. So in general, these particles are different from those coarse aggregates we encounter in railway or pavement, mainly due to its extremely large size. It can weigh easily over 1,000 kilograms, and its diameter can reach nearly 1 meter. And the size and shape properties are the most top concerns of the QA and QC reasons for the local agencies. And a nationwide survey at 2027 ASHTO indicates that the most current state of the practice characterization method is either from hand measurement or visually judging the size. So that's why we have to propose a more objective and standalone way of characterize the size and shape of them. So first, I will introduce the current practice of those two approaches. First, IDOT developed a keystone method by choosing several representative stones of one size category, and by visually judging from the stockpile how does each particle compare with these representative rocks, and then put them into different ranges, gives you a gradation. Then for the hand measurement one, usually you measure the length of 3 orthogonal axes of one particle, and you make some assumption on the rock shape. It's midway between a sphere and a cube. Then calculate the weight, get the gradation. So in general, these two methods are time-consuming, labor-intensive, and subjective. Also, it's not always that accurate because you have the size assumptions like made between a sphere and a cube. That's not always the case. So our methodology is to using imaging techniques to replace the human judge process. So first we'll try to take 3 views of a single rock from top and side. And then based on that image, we need to first extract the particle region from the image, and that process is called image segmentation. After that, we have 3 views of particle. We do reconstruction by intersecting them. That process is called volumetric reconstruction. Then we'll do verification by comparing the reconstruct volume with the ground truth measurement volume. I will start introducing the color-based image segmentation algorithms. So most of the image segmentation tasks are usually completed by using the color information because during the previous years, the segmentation are actually done by dealing with the grayscale images, but that's not enough information. So the community turns out to use color information. And just like we can locate a point in 3D by 3D coordinates in a space, we can actually also use such 3D point to locate a color in the color space. For example, the RGB space, HSV space, and CIE-LAB space are many popular color space we are using. The image analyzer located here are actually using the HSV space. So, but for this project, we are actually using the CIE-LAB space. And the reason why is this color space has one great advantage on the others because it can identify a color correctly under different lightness condition. So think of the image analyzer has 3 lighting position for one particles, so that in the laboratory condition the light is well controlled. But in the field you cannot easily fine-tune the lighting condition. You can just get adapt to what is there. And this color space, as I mentioned, actually can correctly identify the chroma of the value, whether it's in very bright condition or normal light condition or in shadow condition. This is a good illustration of that. So take this image for example. Actually, you will see the rock surface are some part highlighted and some part in shadow. So like a traditional segmentation based on other color space will actually separate them together, identifying that as two or more particles. But using this LAB space by separating them into L, A, and B, you can see in the B channel, the particle stands out from the background, and that provides some intrinsic convenience for the following segmentation. Then here is some details, but I will skip it. The main idea is from the image we can pick representative foreground and background average pixel value and do the gamma correction. That's basically a power enhancement of the image, and this will lead us to the right image. That's a contrast enhanced image, so that's easier for the color segmentation task. Then we apply adaptive thresholding and some morphological operations to get a clean mask. The region is called a mask for an image. A clean mask of the rock region in an image. As can be seen, the robustness of using such color space and the series of operations actually handles the shadow effect very well. Then we are going to the 3D volumetric reconstruction algorithm. So by taking those three views, we get three masks, three silhouettes of the rock. And at the very beginning, we also have a calibration object as a calibration ball before doing the imaging for the rock. And then we use that to calibrate the size of the rock and align them from three directions. Then we do spatial intersection to get the 3D reconstruct volume, and by voxel counting and apply volume correction to get the final volume of that. So compare with the image analyzer, which is doing with 2D, actually the information we are having now is a superset of the 2D information, because on top of the flag and elongation ratio, angularity, surface texture, we now also have its centroid, equivalent diameter, surface area, volume, etc. So, but there is one final step. We need to get the real volume of the rock. That's achieved by doing the ratio between the object and the referencing object. So the ball, the calibration ball is of known size, and we also have is the voxel ratio between rock and ball. By this relation, we can get the real volume of the rock. Then I will introduce the field imaging setup and some ground truth validation. So we designed an easy-to-use and portable framework for the engineers to do such tasks in the field. It is composed by a blue top surface and two blue curtains as the front and side background. They are all hung over a copper tubing framework, which is anchored over an outdoor umbrella base. Then we have the three cameras from the orthogonal, nearly orthogonal directions, and yeah, that's it. So this framework can be easily folded and unfolded at the field. In addition, so for some small to medium-sized large repreps, we also need to use a folding table to ensure certain height of the camera. But for very large particles, usually the table is not needed. And the sample we are collecting is actually from multiple sources. So first one, the source 1 is collected from Vulcan Material Company, which is located here in Atrial. And we pick 40 number of rocks in small size range 3 to 6. And the source 2 and 2 large covers a larger range of the size. Then for each one, since the source 1 rocks are near atrial, we just bring it into the lab and measure its volume by water displacement method. For source 2 and 2 large, we do it on in situ, so we only measure its weight, and an engineer help us measuring its length. That serves as their hand measurements results, and later on we'll do comparison. So for the results, the results will consist of multiple figures. So, but before entering into that, let me first introduce the style we'll be using to present the results. So first of all, on the left figure, it will have 3 points for one rock. That's because for each individual rock, we rotate 3 times and get 3 results. So that's the reason is we need to check the reproducibility of the algorithm, and on the right, their average along with the error bar is plotted. Secondly, the y-axis is the reconstructed volume from the image analysis. X-axis is the measured volume, and there is also a 45-degree line served as a comparison. So over it means overestimation, underneath it means underestimation. And lastly, there is a MAPE term in the legend. You may see that's the error term we use to check the accuracy of our algorithm. So the MAPE is defined as mean absolute percentage error. By skipping over the equations, is actually you have a test result and you have a ground truth result. You calculate the percentage error between them and average that percentage error among all the data points. So for source 1 rocks, since volume is directly measured, the comparison is made between volume. And as can be seen, the MAPE is as low as 5%, and with the averaging result is even lower. That's because we take three replicate tests of one rock, which means you have more views of one rock, and that's more comprehensive information. So for source 2 rocks, since we don't have directly volume measurement, we apply a typical specific gravity value to the volume, and the comparison is made between weight. It can be seen the error here slightly increased. That's because the assumption of the specific gravity actually, when you applies to individual rocks, that may not always be the case, because specific gravity is in terms of a large sampling size of one material. But still, the MAPE error is below 10%. That's very low. And a compilation view of all the source 1, source 2, and source 2 large, all 85 particles are plotted like this. Note that since right now the particle size covers a large range, we add bricks in the both x and y axis to bring them all together in one figure. As can be seen, that most of the data points lie within 10% error band, and all of them lie within 20% error band. So this indicates a very good agreement between our image analysis results and the ground truth results. Also, remember, some engineers are also doing the hand measurements results. We also made comparison between the imaging one and the hand measurement one. This shows the comparison with the current practice accuracy. As can be seen, the hand measurements result has way higher MAPE, even reach 70%, and that can be explained by the high subjectivity and variability of human judging which should be the representative length of one particle. And there can be consistent overestimation or consistent underestimation. Depends on the judgment vary from person to person. Next, we have some summaries of this project. So first, we do literature reviews of the current practice of characterization the reprep material. That's basically visual inspection or hand measurement. And we developed two algorithms, the image segmentation and the volumetric reconstruction algorithm. And their robustness and accuracy are validated against ground truth. So this all in together indicates that the current practice can actually be improved a lot by either using the field imaging system at the current stage or some future development we will make for this project. However, there are still some limitations. For example, it's right now somewhat similar to the image analyzer. It requires you have a blue background. So how to make it background independent? And right now it applies only to single rock. So how can we do a massive rocks? And also a comprehensive database will be highly appreciated for such task. And some future potentials, some potential approaches we are also trying to complete include some scene reconstruction techniques and the using of RGB depth cameras. So this presentation actually summarizes the half-year progress we made on this project. But right now, actually, we are a step further into this one and develop some more exciting results. So I will try to draw a roadmap we have in mind for this project. So first, the stage 0 is the current practice by either measuring the length or visually judging the size. That's a current progress. Then this presentation here made one step further by using the field imaging techniques for single rock and provide a more objective and accurate result on top of the current practice. And then what's our next step? Next step is how to remove such still complex equipment and field setup by only using your smartphone, doing a walk around one single rock and get all the information of it. And then one next step, how can you make one walk around and capture multiple rocks simultaneously? And our final stage, also the ultimate goal of this project, is to if you have a stockpile of rock, how can you do a walk around of the stockpile and try to collect as much as information you can get. So that's the final step, completely non-intrusive and in situ evaluation of the rocks in the quarry. And we actually already stepped a little bit into that, and this is just a preview of the result we generate during that stage. So thanks for your listening, and we hope we'll have more exciting results to update you in the future.
We're gonna have, I think we should have both presentations and then have a round of questions at the very end.
Okay.
So just save your questions.
Okay.
Thank you.
Yep.
Good afternoon, everyone. So I'm going to be the second presenter. My name is Qamhia, and first of all, this presentation is going to be represented after TRB. It was a TLR publication at TRB. It's regarding the evaluation of chemically stabilized quarry by-product applications in base and sub-base layers through accelerated pavement testing. First, I would like to start by acknowledging my co-authors on this paper and presentation. Professor Errol Tutumler, my PhD advisor, Professor Hassan Ozer, who was the co-PI on the project that ultimately led to this paper, Heather Shop from the Illinois Department of Transportation, Sheila Bashir, which was the previous or former TRP chair of this project, but now she's with the Riverstone group, and James Trepanier, who was also the TRP chair of this project. I'll start with an introduction or a motivation why we're doing this work. Basically, we're studying applications for quarry by-products in pavements because due to the high aggregate production in the US and worldwide, which can be as high as almost 1.5 billion metric tons produced just in the US from the 3,700 quarries that operate around the US in 1 year. So with this big number, we expect a lot of materials to be a byproduct of the processes that go into the production of aggregates. It's an estimate in 2013 that around 175 million metric tons of quarry byproduct or QB is generated each year in the United States. So if we look at the numbers in ballpark, then around 12% of aggregate mined is actually waste or quarry byproduct material. And some types of aggregates can have higher percentages than other types of aggregates in terms of the fines that they produce from quarrying operations, such as limestone and dolomite, for example. They usually produce from 20 to 25 fines during the crushing stage. So ultimately, the stockpiling and the disposal of these materials, the quarry byproducts, it can be a very big issue facing the quarries in finding ways to stockpile them. They interfere with their operations, and they require them to buy landfills. So that's why we're studying some applications for this material in pavements. To start with, what is quarry byproduct, or what is the definition of quarry byproducts? Quarry byproducts are also known as quarry fines or quarry dust. These are typically sand-sized materials, so they're less than quarter-inch sieve or 6 millimeter in size. They're sand materials, so they're coarse, medium, and fine sand, as well as little percentage, 12-15% of clay and silt-sized particles passing the number 200 sieve. Where they're produced at the quarries from the different operations such as blasting, crushing, screening, and such. And if you see this picture here, this is a huge mountain of quarry byproducts just from one quarry near the Chicago area in Illinois. And you can imagine how many quarries there are in the US and what are the quantities that are out there of this material to be potentially used. So the motivation of my study is based on a preliminary study that was done before I even jumped in this project. It was a lab study to study the performance of this material, the compressive strength of this material. So first of all, the virgin materials, just the quarry byproducts from different quarries, and in this case from different crushing stages, were collected from one quarry, and they were tested. And if you see these orange, small orange bars here, this is the unconfined compressive strength of the unstabilized materials. If you add 2% cement to this material, or 5 to 10% fly ash, then you can get really high increase in strength and the unconfined compressive strength of materials, up to even 30 times of materials. So since in the lab study there was potential for this material to gain strength as a stabilized material, we were trying to further evaluate that in the field and construct some pavement applications with these stabilized materials. So this is an overview of my test study. It was an accelerated pavement test study, so it was a field performance evaluation for applications of quarry byproduct. What we ended up doing is that we had in total 16 different applications of quarry byproduct studied. So we had a cell here. We divide them into 4 cells, and each cell is basically what marks one location of the accelerated pavement testing device, Atlas, that would be used to test those materials. So first cell here, cell 1, we had a test section studying unbound applications of quarry byproduct, but the main focus of this presentation will be cell 2 and cell 3, which will study the bound or the chemically stabilized applications of quarry byproducts. So if I talk about these applications, we had 7 different applications of quarry byproducts in bound applications, and then 1 conventional aggregate pavement section for comparison. And basically, those applications, if I start with, they're either cement stabilized or fly ash stabilized applications. So if they are cement stabilized, then they're cement stabilized with 3% cement by weight. If it's fly ash, it's 10% fly ash by weight. We have some applications studying a blending of quarry byproducts with other coarse recycled aggregates, such as cell 2 here, section 1, which is 70% Quarry By-Product mixed with 30% fractionated wrap, so the coarse size of wrap, and mixed with 3% cement and used as a base material. Similar, section 2 is 70% Quarry By-Product, but instead of wrap, it's fractionated recycled concrete aggregate now and 3% cement. Cell 2, section 3 here is studying wrap, Quarry By-Product, also 70% QB, 30% wrap, but now with 10% fly ash. So we're varying the material from wrap to RCA to study the effect of the coarse aggregate type, and then we're varying the stabilizer from cement to fly ash to study the effect of the stabilizer. Section 4 here and section 5 are just Quarry By-Product mixed with 3% cement from 2 different sources. So we have QB2 in section 4, and then cell 3 section 1 is QB3, which is a third source or a different source of Quarry By-Product. So we're studying the effect of the source of Quarry By-Product on performance. Then 2 sections here in cell 3, section 2 and section 3 are inverted pavements, in a sense that we're using a cement stabilized or a fly ash stabilized Quarry By-Product subbase, and then on top of it is base material of conventional aggregate dense graded material. And then the last section is regular dense graded aggregate material pavement. So all these sections are bases, are 12 inches bases, and then 4 inches of HMA on top of them, overlaid with 4 inches of HMA. For the 2 inverted sections, there are 6 inches of subbase, 6 inches of base, and then 4 inches of HMA on top. And if you see in 4 of the sections here, cell 2 section 1, cell 2 section 4, cell 2 section 3, cell 3 section 2, sorry, and cell 3 section 4, where I have the X's. These are test sections that we buried some pressure cells, soil pressure cells on top of the subgrade to measure the responses on top of the subgrade, or what is the deviator stress that is being recorded on top of subgrade while we're trafficking the test sections with Atlas. First of all, just briefly describing some of the lab work that was done before the study. So we had to evaluate the materials in the lab, know some characteristics of these materials. Of course, we needed to know the grain size distribution of the materials. So what you see here in red are the Quarry By-Product materials from the 2 sources. Fairly similar gradations, and they're of course the finest gradation of all materials. What you see here in blue are the Quarry By-Product 70% mixed with 30% wrap. So this is the mixed or the blending gradation of the materials. So the one with the full circles here, the one at the bottom, is the one that has the wrap, so it's coarser because the wrap was fractionated wrap, just the coarse aggregate, while the RCA had some fines in it. And then the coarsest material, of course, is the CA6 gradation material, which is a dense graded aggregate material that we use for like the conventional test section as well as the base materials in the inverted sections. Another thing or study that we did is the compaction properties to get the optimum moisture content and maximum dry density. And the idea here was for each material or test section constructed, we wanted to construct it at its optimum moisture content to achieve as high density as we can and a better packing of the material. So we had third test is the unconfined compressive strength for the different combinations of materials that were used to construct the test sections. So if you guys followed with my description of test section, we had ultimately 6 different combinations. 3 of those combinations were just Quarry By-Product with cement or fly ash, Quarry By-Product with cement from 2 sources, and then the other 3 were the Quarry By-Product mixed with a recycled coarse aggregate such as FRCA or FRAP, and then the FRAP ones had either cement or fly ash stabilization. If you look at the results and with the t-test statistical analysis, then the results are statistically different for the ones or the samples that had the Quarry By-Product mixed with the coarse recycled aggregates. So they had higher strength that was statistically higher than other samples, while the Quarry By-Products with cement and fly ash in the lab, they were statistically similar. So there was no statistical difference when just Quarry By-Product was stabilized by itself. Now moving to the field construction and all the quality assurance, quality control tasks that were done in the field. Of course, the first task was to engineer the subgrade, so we wanted to build those pavements on top of somehow uniform or consistent subgrade between the different sections so that we're ultimately comparing the performance of the bases and the subbases more than anything else. So we engineered the subgrade to a CBR6 subgrade, and we did that with DCP and some back calculation of the CBR from the DCPs. And then after the subgrade engineering, we had the construction of the base and the subbase layers. So we had to ensure the uniform mixing, compaction, and optimal motion content, and then quality checks on the different layers. So we had the nuclear density gauge to measure the density of each constructed layer, geogauge and lightweight deflectometer to measure the stiffness basically of those layers, and also to monitor the curing of the stabilized layers. Now I'm just showing here the procedure, or the step-by-step procedure that we use to construct the stabilized layers. So of course, here we're talking about accelerated pavement testing. So we're talking about very small sections, like 40 feet, 20 to 40 feet long, and 12 feet wide sections. So with those small quantities, it's not easy to get a full train to construct the test sections or do a plant mix and bring it to the plant just because of the limited quantities. So we had to control the quality as much as we can. And what we did here basically is that we isolated the stockpiles for each section. We mixed that uniformly with a backhoe to get a uniform moisture or existing moisture content. We measured that moisture content. Then we mixed again. We added the cement. We did the dry mixing of the materials. Then we added the water to the optimal moisture content. We did the wet mixing, dumped them on the truck, take them to the construction site, which was fairly close, like within the same area. Then till the material again using a soil size tiller to ensure better uniformity, and then compact the test sections. Here I'm just showing some results for the QA/QC of the test sections. So this is the average subgrade CBR that was measured in the different sections for cell 2. This is the triangles here, and then cell 3. So this dashed line at 6% was the target CBR that we had, and we were fairly about that CBR minimum of almost 4.8 or 5, and maximum of 8 for all the test sections and all the different points that we had for control. Also, this is for the achieved density and moisture contents for the different test sections. So the density is shown in the bars here, and then the moisture content is the black line, and we were also fairly on target for densities and above 95% density for all. I'm not showing the densities or the moisture contents for the base layers, but what I'm showing here is some monitoring of the curing of the test sections. And basically this was done using a lightweight deflectometer. And the way we did it is, since those sections before they were paved, they were exposed for some time, up to 11 days in some of the cases. So we were doing lightweight deflectometer drops frequently, every day or sometimes twice a day, and get measurements of what is the modulus of these test sections. If you look here, this section, this is cell 2, section 1. This is the QB with the RAB, with the cement mix. That was the strongest section by far in terms of modulus, followed by the one that had the RCA, and then the one that had just the cement treated QB. And this is also the cement treated QB from cell 3. This fly ash here is coming as the lower section. Also, these are the inverted pavements just on top of the inverted pavement, 6-inch inverted pavement on top of the subgrade, and then that red dot here is a final measurement of the lightweight deflectometer back-calculated modulus of the conventional aggregate section. So after the test sections were constructed and the QA/QC were checked, we started the experiment, the accelerated pavement testing experiment to monitor the performance of the test sections. Basically what we had a white base tire doing the trafficking using a 5 miles per hour speed. Tire load was to start with 10 kip, 110 psi tire pressure. We did 100,000 cycles at these load levels, and then we had some similar performance, and we were not able to fail those test sections, so we decided to bump up the load and the pressure a little bit more and continue the trafficking for a little bit more to see if we can differentiate the performance more. So we went up to 14,000 pounds load, 14 kip, and 125 tire pressure, psi tire pressure for the next 35,000 passes. And here I'm just showing that there were some pressure cells, as I explained before. So basically, this slide here shows a summary of all the surface rut profiles from all the different test sections that were tested. And as you see, the rut profiles were taken at frequent number of passes, up to 135,000 passes, and this is at 100,000 passes where the load and the pressure of the tire were bumped or increased. So if we see those two lower points here, two graphs, those are actually the first two sections in cell 2, which are the ones that have the quarry by-product with wrap and cement, or quarry by-product with RCA and cement. And if you look at the surface rut after 135,000 passes, that was a little bit over 2 millimeters of rutting only. So our threshold was around ½ inch of surface rutting to stop the experiment, which is typical, like ½ inch to 1 inch. For low volume load, it's more typical as 1 inch surface rut. That's when you consider your pavement failed. So we had ½ inch, and with 135,000 passes, we only got much lower than that. Our conventional aggregate test section had rut accumulation very fast, higher compared to the other sections. And if you see, when we bump the load here, you can see most of the sections had an increase in the rutting rate. So they were rutting at a faster pace than at the low load level, which is expected, and that's why this was done in the first place. The only section from the stabilized section that surpassed the threshold of ½ inch was this section here, the inverted pavement that had the fly ash subbase and then the conventional aggregate base. But still, if you look at the number of passes, we're talking about around 130,000 passes at very high load levels, so that was also can be considered good performance. This is the slide that shows what were the pressures on top of the subgrade measured for the test sections here that are shown with the red X's. And if you see the three sections here, those are actually the sections with the stabilized applications. And this section here where you're getting up to 60 kilopascal or around 9 psi subgrade pressures, this is the conventional test section that was tested at the end. So basically, we're seeing that the subgrade pressure in the conventional section were significantly higher than, or was significantly higher than those that were in the stabilized layer. Part of the reason is because we find eventually that the conventional section was constructed with lower thickness of HMA, and also it was a little bit highly porous HMA than the other sections, but still that's a big difference in subgrade pressure, and this is a significantly low pressure, like 20 psi subgrade pressure with just 12 inches of base and 4 inches of HMA is considered very low, and that's what we will see later, that we didn't see any subgrade running in those test sections. I'm not going to go over this table much, but this is a summary of all the test sections ranked by performance, so the best ranked section to the lowest ranked section. And these are the different properties that were measured for the HMA densities, the thicknesses of the layers, composite modulus of the base material, and what are the subgrade pressures that were. I kind of covered most of the details in the previous slides. So before we move to the next part of my presentation, I just want to highlight the key findings on performance from the accelerated pavement testing study. So basically, the test sections that were stabilized with cement had better performance and less variability than those stabilized with Class C fly ash. And only section that accumulated more than ½ inch of rutting was one that had a subbase of QB mixed with fly ash. The ones that had recycled aggregates, recycled coarse aggregates, wrap and RCA, performed the best out of all the test sections. We tested two QB sources that were cell 2 section 4 and cell 3 section 1. Those had fairly similar performance in rutting. So there was, in this study in particular, we didn't see a big difference in rutting performance from two sources of aggregates. I already talked about this, that the rutting rate increased when the wheel load was increased, and also there was an increase in pressure when the wheel load was increased. And the premature failure of the test section with rutting and fatigue is due to failure of the material because of the thickness of the material as well as the porosity of the HMA, but still overall it had a higher pressure on top of the subgrade transmitted to the subgrade. The second part, I'm going to talk about the post-APT testing and activities that were done. These are not in particular order, but we did HMA coring for the test sections. We also did trenching to expose the test sections and take accurate measurements of the thicknesses of each of the the subsurface materials. And we also did FWD, of course, before the trenching and the coring to get the surface deflections and back calculate the layer modeling. And we also did a DCP testing through the course. So once we took the HMA course, we were able to use a DCP, drop the DCP, and see how stiff the base and sub-base layers are, the stabilized layers, by dropping the DCP and seeing how much basically blows it's going to take to penetrate the whole depth of that base or sub-base material. So quickly showing the results from these activities. So by trenching and coring, we were able to get what were the thicknesses in each layer, which is important later on because we're doing some modeling on the test sections to measure responses and such. So we need to know those thicknesses, and also for FWD back calculation purposes. These are some pictures from the trenches that we had. So basically, this is the strongest section in cell 2, which is the section that had the Quarry By-Product mixed with the wrap. You can see the wrap here, black dots maybe, and cement. And we were actually able even to extract some chunks of materials, stabilized materials that are intact, and we were able to later on cut them into cubes and test their strength from the field study. This is the one that had the fly ash in cell 2. One of the inverted pavement test sections with this fly ash treated subbase in cell 3, and then the last one here where you see the highest surface rutting is the conventional test section in cell 3, which we'll talk about. This also had shallow water table. Now showing some results for FWD, and here only showing the center FWD deflections for comparison for the different test sections. So each bar in each test section is showing one occasion when FWD was conducted. So we did 3 times for most of the test sections after the construction, before we traffic the test sections, and then after the trafficking of the test sections. So if we just look at the ballpark of the numbers for each section individually, so each 2 points here are one section in each cell. So this is the section 1 in cell 2, this is section 2, this is section 3, and then this is section 4. So you can see that the FWD deflections pretty much they follow the trends in the rutting or surface rutting that were measured before. So these sections here, the ones that have the wrap and the RCA with the cement, had the lowest FWD surface deflections. We're talking about 8 to 10 mils almost of deflection. That's a very low deflection. The fly ash one, which was the worst performance cell 2, had the highest, and then this is just this. So they follow the modulus back calculated, the trends for the modulus back calculated from LWD, as well as the rutting trends on the surface. This is similar for cell 3, but the scale here is different because of some of the high deflections in the last 2 sections, which are the control section and the one that had the stabilized fly ash. If you look also at the ballpark numbers in each section, they also match the rutting trends that were measured, as well as the FWD deflections. So these are the one inverted pavement with cement, and then this is the section that had the fly ash inverted pavement that accumulated more than half an inch of rutting, and then this is the conventional aggregate base section that had the premature failure. Almost the last thing I'm covering here is the DCP results. So the way the DCP results are presented in each test section is the number of DCP drops per 1 inch of penetration. So since we know the thicknesses of our layers, we were able to penetrate the whole layers of the aggregate bases. And then instead of reporting penetration rate or how much penetration we get per drop, because that number is very low, we're reporting the number of drops to penetrate 1 inch in the layer. And if you see those, like this section here, that's the section that had the FRAP and the QB. That was the strongest section, the best performer, along with this section, and they had the highest number of drops required to penetrate 1 inch in the material. So overall, if you look at the trends here that we have, they follow the trends of the rutting very closely. And I have an example here for you. So these are the rutting values taken, I believe, after 40,000 passes. And what are the penetration rates? So you see that the higher the number of drops to penetrate 1 inch, then the lower is the deflection, the surface deflection is, and this is consistent for all of the test sections. Last slide here before I jump to the conclusion is the depth of water table. We also measured that to see if that had an effect on the performance. So pretty much our water tables were deep. They were around the 44 to 53 inches deep. That's from the surface of the pavement, from the surface of the HMA. Also this last one here, cell 3 section 4, that's the conventional aggregate control section, had the shallowest water table, and that's probably also because of the low HMA thickness and high porosity HMA, which led to more water penetrating through the pavement and going into the subgrade. Lastly, findings and conclusions from this study. I kind of went over these during my presentation, but just to iterate or to highlight them. So the sections that had Quarry By-Products blended with RAP and RCA showed the best performance, and there was not significant difference in performance between RAP and RCA in this particular study. The premature failure of the control section was attributed to the low HMA thickness and the shallowest water table. Sections stabilized with cement had better performance than those that were stabilized with fly ash, due also to the variability of fly ash that can come with the source. The thickness of the subsurface and the HMA layer, of course, have a significant effect on the performance, so we need to consider that in the design of those layers and in the mechanistic analysis of the results and such. Cement stabilized layers of two QB sources that we used, QB2 and QB3 here, they showed similar good performance, so we didn't see in this particular study difference in performance between two different sources. And lastly, that inverted pavement sections, especially the cement stabilized one, had good performance. So before I acknowledge people who helped me with this project, I would like to tell you what the next steps were in this project. So three main things that we've been proceeding with. The first thing is the mechanistic analysis of the results, FWD results, and then getting equivalent test sections, because we saw that these sections had the same targeted design thicknesses, but their performance was different. So what if we want to get a certain performance out of these test sections? What are the thicknesses that we should target? What are the thicknesses that should be designed? So we had that through mechanistic analysis. The second part is how sustainable these applications are, and are we expecting any environmental impacts, like reduction in emissions? Are we expecting any cost savings from these applications after they are applied? So we did that study. We did a life cycle assessment and life cycle cost analysis study. The third direction that we're moving in is that how durable these materials are. So we showed that here they survived 2 or 3 winters, maybe, and even harsh winters, some freeze-thaw cycles, but how durable they are, like if they're consistently being studied. And that's a study that we're pursuing now for the durability of these materials with freeze-thaw testing and with wet-dry testing. So how sensitive they're going to be to change in moisture content as well as to freezing and thawing cycles. So lastly, to acknowledge people who worked on this project. Professor Al-Qadi helped us with the pressure sensor installation and other stuff. I got a great help from everybody here at HRL, in Professor Tutubi's group and Professor Al-Qadi's group during the construction. Also the research engineers, Greg, Michael Johnson, James Meister, and Cheng Wawu, and of course Mark helped a lot with this project. With that, I end my presentation. Thank you very much.
I think we don't have too much time for questions, maybe a couple for each of the presenters. Zichi.
So yeah, I have a question. Well, one general question for Huang. So you are using like the color map, the color image processing to identify the rocks and its information. But because when you're taking the picture, you still have this background. So why don't you choose a background that have a very contrast color to the stone and still use the grayscale image to do some, I mean, like high pass filter to identify the edges of the rocks? Will that be like simpler, or is there any advantage underneath the method that you're proposing?
Okay, that's a good question. So actually, if in the lab, we can actually do what you are proposing, but actually the most challenging thing in field is like we cannot control so much parameters. Like if the lighting, like shooting on your background, for example, I think you are suggesting black background to make the contrast. So you will have some part very highlighted, and the light are unevenly distributed along the background. And another thing is that the rock color is not always distinguishable in like grayscale. For example, you can have black rocks, right? So the blue background, there is one reason for choosing that, because that's the most distance from the regular color of rock. Yeah.
Julie?
I was just wondering if you could let us know what is the main motivation of having this setup in the field. I know the system that we have is smaller, but could you let us know what's the motivation of creating a setup like this in the field?
Okay, so the initial idea is to try to transfer that image analyzer setup into the field, and it needs to be portable and easy to use, not a very fixed setup for the engineer to use. But I think your question is actually our next steps by removing that complex equipment, because we are trying to just using one smartphone, and because we're still thinking even with the easier to use equipment, it's not that easier for the engineers. So the most easiest thing is to use nothing, just a camera. Yeah.
Any more questions? Yes.
So I have a question. So if I understood it correctly, so you are taking 3 pictures, right? X, Y, Z direction. So are you assuming that the sides that you are taking and the contrast side is are assuming they are the same? Like with respect to the surface you are taking.
Oh, you are saying that the front and the behind view are the same.
Yeah.
Oh, yeah. Actually, so if you seeing an object from one view, and if you go to the another view, you will the silhouette will be exactly the same, right? If you are looking from two directions on the same line, very close, very precisely, they will see exactly the same boundary and silhouette of the object.
But even you have same boundary, you may have different.
Yeah, the surface look may be different.
Yeah.
But I see where you are coming from. Yeah, there is some error between because when you are lying by 3 directions, actually you are still missing some information of some little textures of the rock. Yeah, that's it. And that's why for the following steps we have take multiple views of one rock, and that construction will be more accurate than this. 3 view is always limited.
Thank you.
Again, I agree with his comments, Huang's comments. When you think about when you go out in the field, you have to start from the same step that you're very familiar and you have developed things in the lab, right? That was kind of our first initiative here in this case, what he presented. And as he said, this is only 6 months into the research project. That's the first thing we did. And with the 3 orthogonal views, now you can create the volume, the particle. You can create the 3D particle shape and the volume reconstruction. And that's what he was showing in this. But then as we were doing that, we found out that there are so many things that currently done by hand and by the current practice that actually is kind of rudimentary or quite open to all kinds of errors, like hand measurements he showed, right? So how can we actually automate this for machine vision in the future? And of course, with just quick videos, walk around, that's where we're going with this. Going back to the color cameras, pitch black is exactly what would be the hardest for you with a black background. Because we had a black background in the original version of the image analyzer before, and we were very happy passing on those conveyor belts, actually the white color, whitish color, whatever, limestones and dolomites in the state, right? But when we started doing more railroad ballast things, we had granites, basalt, and other types. They were quite dark color. So it's very difficult to establish the contrast, whereas color cameras already do that. There's no blue rock around. There's a red rock, but not a blue rock around.
Okay, let's thank our presenters.
Leaving now, yeah.
Wait, are you gonna get some? Are you buying?
I might, yeah.
I mean, I don't want you to specifically go there. You will.
If I will,
I just need
I will let you know. If I can't let you know, I'll get you.
No. I don't want you to specifically go there.
Okay. I won't get it for Javier.
I'm being serious. Again,
I try to find
If I go, seller or seller.
no.
No ideas about how to do this. And one of the items is just like tripod, which you can show me on the slide to lift it up. But even that is so time consuming anyway.
Yes, it's more than 2 plus. 2 plus.
Trying to get the rock you
2 plus.
put on.
这样的话，它有可能会 override，
Arbitrary figures.
但是它不可能永远
Okay, the work is memories and do that awfully.
Oh, that's not good.
2 plus.
Oh, it's
Mississippi or other rivers.
No, you look bored yourself. That's what she's saying. Somehow fit it into the presentation was bored.
More in the lower, that's the right size.
You've been more.
How do you do that? Again, that's been something for years. I've been
But specifically,
imaging the rock.
你相当于就是这个角度，这个角度只有这个角度。
no, but still.
I think that's because
Still.
If you go there more, size rock.
装在一起，大家一起选择这个。
How can you get multiple the video, and then by just analyzing the video, almost like a here's the weight distribution. How do you come up with that? And with the side part, there's an angle. And what you see on the surface is only a certain portion of the rock. How do you know? You have no idea how it actually extends deeper into the pile. Right? So,
你只要2D 的。
and we're trying to come up with machine learning ways, neural networks, deep learning, whatever nowadays they call it.
这个
Building machine vision into it.
Yeah, but still, machine validation is how we're going to do. I mean, that's the one. I mean, I did some work.
Validations again by known rocks, by known piles, exactly the different ways that actually on the surface, right?
它对雷达一点都不懂，所以它就有的问题，它可能它是无意问题，但是一不小心就一棒打到我们门上面，有没有？就是因为他对这个东西。